Okay, so we are recording now. So we're going to talk about section 7.4. We're going to talk about exponential growth and decay. And just a comment, so in the textbook, the section 7.5 and 7.6 are optional sections. Section 7.5 deals with the logistic equation. It applies to populations, for instance, and other things. Logistic differential equations. 7.5, and 7.6 deals with what are called predator-prey systems, where you have competing species for resources, and you have differential equations that involve like terms. I'm trying to recall. They have like terms that can affect both populations. So it's a fascinating material, section 7.5 and 7.6. We probably won't have a chance to cover it, but if you take Math 282 differential equations, you will see those there. Right now, we're going to now cover section 7.4. Let me give you a moment to copy this example down. Okay. Okay, I'll give you another moment here. Okay, so here we have a common inhabitant of human intestines is the bacterium Escherichia. I'm probably not pronouncing that right. It's called E. coli. How many have heard of E. coli before?
Yep.
Okay.
Escherichia, just so you know, Professor, we call it Escherichia coli.
Clay, I'll go with your pronunciation. Sounds good. All right, very good, very good. And let me just see here. Okay, so a cell of this bacterium in a nutrient broth medium divides into two cells every 20 minutes. The initial population of a culture is 60 cells. Now, we want to find an expression for the number of cells after t hours, and then to find the rate of growth after t hours. Okay, so all right, how many recall these kind of problems in pre-calculus where you have, like this would be exponential growth? How many of these problems have you seen ones like these, like in maybe pre-calculus? All right, Clay has, and I mean, I know in pre-calculus, at least in Montgomery College, they teach this. But what we, sorry, go ahead.
Oh, sorry. I just want to say, I actually remember this doing in Calc 1, not pre-calc.
Okay, okay. Well, absolutely, absolutely. And you know, the number of cells, we're going to call that y. Okay, so what we need is a differential equation that models this exponential growth. And the differential equation is going to be dy dt equals k times y. Okay, that's the differential equation. And we have an initial condition that at time 0, the initial population is 60 cells. Okay, so in section 7.4, the problems all are going to be have differential equations of this kind of form. This means that the growth rate of the population, is proportional to the population size. So at time t. So as the population gets larger, the growth rate gets larger. And that's why bacteria like E. coli, we're always very worried about that. Restaurants and so forth are worried about that. We have, you know, a health department that monitors these restaurants for things like this, because a lot of people will get sick, right? If that happens. How many have heard, like in the news, about, like, for instance, recalls of beef or recalls of eggs, or that sort of thing from time to time? On the news, there's a big recall, like of eggs or something like that. How many have, or you know, if you bought this baby food, and there's a recall. Has anybody ever seen that kind of thing? Sure, and it's because it's very serious. E. coli can spread quickly. All right. So what we want to do is we want to solve this differential equation. We're gonna start there, and actually for this problem we're actually have two pieces of it. Well, let me see here. Let me just see here. All right, we have to solve the differential equation. So let me go to the whiteboard. Let me go to the whiteboard and let's solve this right here. Let me clear this off here. Clear the annotations. Okay. So, all right. And I learned here that I can adjust this. Let me see. What's that going to look? Oh, that's too fat there. That's too fat. Hold on. I can adjust my font. Niat showed me this. All right. I might maybe make it 4. Okay. So let's put it in black. So dy dt is equal to k times y. Let's start there. Now, is this differential equation separable? Yeah. It is. It is indeed. So what we'll do, thank you, Clea, thank you, Jonathan, thank you. So we'll, you know, I tend to like to have my y variables on the left side of the equation. So let me multiply through by dt. And if I do that, I'll get dy equals k times y dt. And now what we'll do is we'll multiply both sides by 1 over y. And when we do that, we'll get 1 over y. So we're doing the solution here. This is the solution. Okay, you can write it in your notes. 1 over y dy. And let me see here. The y's here simplify out, right? So 1 over y dy equals k, I'd like that in black, equals k dt. Clea, question?
Yeah, so just to make sure, like, isn't it, if we like multiply with 1 over y, isn't it the same as dividing by y?
Sure,
Okay.
absolutely. Yeah, you can think about dividing both sides by y. That's the same as multiplying by the fraction 1 over y. Sure. And you know, now here we are. What are we going to do to both sides of the now we've separated the variables. We've separated the variables here. What are we going to do to both sides of the equation? Integrate both sides. That's right, Jonathan. We're going to integrate both sides. So let me go up here. We have the integral of 1 over y dy equals the integral of k dt. What's the antiderivative of 1 over y?
ln,
Good.
the absolute
Ln of
value.
y. Right. And on the right side, the antiderivative of k would just be k times t. And then we have our little constant of integration here. So we know that what we did was we had a constant of integration on the left side, and then the right side, we combine them and we just get a constant. Now it turns out in this case, okay, since you know the y, I mean, what y is the population of E. coli. Y is the population of E. coli after after T hours, right? So again, we're saying that the growth rate of the population of E. coli is proportional. When you say proportional, you insert a K. The growth rate of the E. coli is proportional to the size of the E. coli population at any given time. So, well, can population ever be negative?
No.
No. So y is greater than 0. So this means the log of the absolute value of y. Good. Thank you for the input, everybody. The log of the absolute value of y just is then the log of y. That equals kt plus c1. That gets us here. Now, what are we going to do? We want to find out what y is. Okay, we're going to exponentiate both sides. Good, Franklin. We'll exponentiate both sides. And when we do that, we'll get y equals e to the kt power times, hold on here, e to the kt power times e to the c1 power. And e to the c1 power I'll call c2. So now we have, yeah, and when we say y, of course we mean y of t, right? We mean y of t. So y is equal now to this C2 constant times e to the kt power. This is where we're at here. This is where we're at. And so the how many constants do we have here in this formula for the population y?
2.
2. And naturally, that's right. And we want to solve for those constants. The formula's not, it's not really, I mean, it's a family of solutions, right? But we want to find out what those constants are. So we need two pieces of information. Well, we were given that initially, how many cells, how many E. coli cells are there initially? 60. That's right, Susanna. So y of 0 equals 60. So what we can do, right, is we can take 60 and we can try to solve for one of the constants. So 60 equals C2 times e to the k times 0. So 60 then equals C2 times e to the 0, but that's just C2 times 1. So C2 equals 60. C2 equals 60, and this implies that y is equal to 60 times e to the kt power. Okay, that's what that means. So in other words, we found out what one of the constants is. Okay, we found out what one of the constants is. Now we got to find the other constants. So are there any questions so far on what you're seeing there? Yeah, it's a little hard, I know. I'll tell you what, Mohammed, let me go to the notes. I mean, these are notes, but let me go now to the uploaded notes. Where we're at is we've determined that C2 is equal to 60. Okay, and now I'll go to the notes if we're good. Is everybody good? Nia, question? You have a question? Oh, you're good. Okay,
Yeah,
Nia's good.
no, I have a question.
Okay. Oh, okay.
How did we come up with the first equation?
For the problems in section 6, so like for the problems in section 7.4, the differential equations are going to be of this form: dy dt equals k times y. And you'll see that differential equation, well, look what happened. Look what happened. We solved the differential equation. We solved the differential equation, and we ended up getting y equals a constant C2 times e to the ktth power. How many recall, hey, that reminds me of those exponential growth models that I studied in pre-calculus. In pre-calculus, what you were given with exponential growth type models is you were given this this equation, right? You were just given this equation, but now you know where that equation comes from. It comes from the differential equation. So for exponential growth and decay models, the rate of growth is proportional to the size of the population. And so all the problems in section 7.4 you can use that differential equation, dy dt equals k times y. Okay. All right. All right. Well, let's see here. Now let's go back to the thing here. So now, you know, we're working on this problem here. And, you know, if you blow it up a little bit here, I mean, here's where we're at. Here's where we're at. Well, what I've done here, this here is what I showed you in the whiteboard. Okay, that's what I showed you in the whiteboard. And make that, hold on here, class. Let me move this over just a little bit. And Mark, so how did I get that C2 is 60? I don't know why this is not. Hold on. Let's get this down a little. Let me get this down, font down a little bit. Yeah, so, okay, hold on here. Let me just clear the annotation. So this is what just I showed you in the whiteboard. Y equals C2 times e to the k-th power. Now we're given that at time 0, initially there's 60 cells. So I take 60 and I substitute it in for the y here. So y is 60. C2 stays C2. And then time equals 0. So time is 0. That's right here. So I determine that C2 is 60. Therefore, y of t is 60 times e to the k-th power. Mark, are you okay with that? Okay, good. You're welcome. You're welcome. Well, we have to find this value of k. So k, this k here is what's called, this k is what's called a relative growth rate, because it determines how fast this population grows. Well, we have to figure out how we have to get that. Well, there was another piece of information in the problem that said that the cell divides into 2 cells every 20 minutes. Okay, so like if we let, you know, 20 minutes, of course, is 1/3 of an hour. 1/3 of an hour. So I guess in this problem, I may have I want to make sure, let me just go to the whiteboard real quick. Let me just go to the whiteboard. I want to go back to what I showed you there. Yeah, T hours. Okay, that's right. That's right. T hours. That's consistent. So hold on here. Let me go back now into this here. Okay, good. Okay, so the new blackboard, it saves the highlights. It saves what's there. That's good. So the formula for this is man, hold on, I got to get this down a little bit here. Okay, the formula for this assumes that t is in hours. So 20 minutes is 1/3 of an hour. So what I do is I say, okay, well, okay, let's let time equal 1/3 of an hour. Let's let time equal 1/3 of an hour. Well, the population is going to double then, right? Because it says the population doubles. Well, the one cell divides into 2 cells every 20 minutes. So that means if we start out with 60, 60 cells initially, then after 1/3 of an hour, that number of cells will double to 120. And so this means then that, well, if I divide both sides by 2 here, if I divide both sides by 2, I'll get then that 2 equals e to the 1/3 k power. Okay, that's not a negative 1/3. That's a positive 1/3. So what we have to do, of course, is we have to solve for k. We have to solve for k, and I know there's a question here. So you know, again, here it is: 2 equals e to the 1/3 k power. Yes, Clea. Yep.
So just so I understand, like I'm understanding this right, so 120 is from, we had 60 and then it doubled, right?
Well, yeah, we started out with 60 cells, and after 1/3 of an hour, 20 minutes, which is 1/3 of an hour, that population doubles to 120.
Okay. My next question is, why do we use like 20 minutes? Why do we use it in hours, or do we need
They're
it in
trying to
minutes?
trick you. They're trying to trick you. That's basically, I hear what you're saying. Well, you know, scientists, they're not really trying to trick you, but they're trying to, you know, if they say, hey, you know, 20 minutes, some students will put in 20 minutes and get the wrong answer. And then, oh, why'd that happen? And then, oh, yeah. The way I defined my population was, y is the population after t hours. So you got to go back and change 20 minutes to 1/3 of an hour. So it makes life a little, just, you know, it's just kind of to test you a little bit. You know, so you're saying it'd be nicer if they gave you just hours to begin with, 1/3 of an hour instead of 20 minutes, right?
Yeah, but yeah.
But you know, you're in calculus 2 now, so they'll you know, you know, if you're out there you know, at NIH or something, and somebody gives you a report and they give the time in minutes, well, you know, you got to know to convert that to hours if your formula is for hours. So it's good practice. Good question. And so now, of course, we want to solve for k. We want to solve for k. So I'm going to take the log of both sides of this equation here. And then that's going to get me that the log of 2 equals 1/3 times k. And that gets me here. And now I can solve for k. K will equal 3 times the log of 2. But we want to write 3 times the log of 2 as log of 2 to the 3rd power. Now, why is that true? Well, remember from your algebra days, if you have the log of a to the bth power, that will equal b times the log of a. So I can write 3 times the log of 2 then as the log of 2 to the 3rd power, and then that equals the log of 8, the natural log of 8. And it's much better to use the natural log of 8, because now so my relative growth rate, k, is the natural log of 8, and that's what I'm going to go ahead and put in here for the k. Hold on here. Hold on, this is not erasing the way I want it to. It's because it's thinner. That's okay. Right, natural log of 8. So this here is my k, and look at what we can do. We can take, hold on here, we can take the log of 8 times t. Well, what I'm trying to say is we rewrite this e to the power log of 8 times t, and we can write it as e to the log of 8 raised to the tth power. Now, why is that nice? Because e to the log of 8 then just becomes 8. And so y of t will equal then 60 times 8 to the teeth power, where t is greater than 0. Now you have a very nice formula that gives you an intuitive feel for how fast this this population of E. coli is growing. Let me see. Was there a question? Was there a question? You could use 3 times the log of 2. WebAssign. So Jonathan, WebAssign would accept 3 times the log of 2. It would. And even in your answer, I think it would accept it. But it's better to write it to just write 3 times the log of 2 is the log of 8, because then you get a very nice formula here. That's understandable for your population of E. coli. Yes, Nia, question?
Professor, could you explain again why we doubled the population of E. coli after 20 minutes?
Well, in the problem, when you copied the problem down, it said that go back here to the whoops, hold on. It says that a cell divides into 2 cells every 20 minutes, okay, or every third of an hour. And you're starting out with 60 cells. So after 1/3 of an hour, 60 cells would become 120 cells, right? Because every cell divides into 2 after 1/3 of an hour. So 60 cells would become 120 cells. And so, yeah, does that make sense?
Yeah.
All right, very good, very good. So, okay, well now we have our formula. We have our beautiful formula here to model the population growth of E. coli. Here it is, right there. And but the problem now says so we found an expression for the number of cells after T hours. Now the problem says find the rate of growth after T hours, the rate of growth. So if we want to find the rate of growth, what are we looking for? Rate of growth is a what? Oh, well, go the other way, Mohammed. The rate of growth would
Exponential?
be a rate of when in calculus, when you hear rate, you think derivative.
Oh,
So
yeah.
there you go. That's right, Mohammed. That's right, Victoria. All right. So we need to take this formula and differentiate it with respect to t. Okay, and that's what we're doing now in the next page. So remember what dy dt was. Okay, remember what dy dt was. Dy dt was equal to k times y. Well, let me just see here. So, all right, so y, I want to say this the right way. Hold on here, one moment. Yeah, this is good, this is good. So, I want to be a little careful here. So this here, now I'm not doing this the way I want to do this. Give me just one moment here. dy of t equals k times y. The k is the log of 8. And y is 60 times 8 to the teeth power. Okay, so we're doing fine. We're doing fine. So you know, here's dy dt, and we know dy dt is k times y. That's the differential equation. Now, the relative growth rate k is equal to the log of 8. Y is equal to 60 times 8 to the 10th power. So that's how I come up with this statement here, that dy dt is, well, I mean, I can do a little rearranging here. This here equals 60 times the natural log of 8 times 8 to the 10th power, right? And so that's how we end up getting this statement here. So I know now my rate of growth. And after 10 hours, okay, after 10 hours, right, what I have to do is substitute in 10 for the t here. And so dy dt, evaluated when t equals 10, okay, this is notation you should have seen in Calculus 1. That's just going to be equal to 60 times the natural log of 8 times 8 to the 10th power. If you put that in on your calculator, okay, at least when I did it, it put the answer in scientific notation. So like if I, maybe let me just sort of do it on my TI calculator now. I'm wondering, let me see, let me try Desmos. Let me see what Desmos does here with this. Yes, Mohammed, question?
I had a question of like, so I don't really understand how we set up the initial equation, like when we did dy dt equals ky dt. Like how do we figure out what to integrate?
Well, you separate the variables on that, and then that determines, well, we did it once, but actually there's a formula. There's a formula that we can utilize specifically for section 7.4. All of the problems in 7.4 can, if you separate the variables, they will become this formula. And I will show you that in just a moment. All right, Mohammed, I'm glad you asked that question.
All right, sounds good. Thank you.
All right, all right. So what I'm doing in Desmos is I'm typing in 60 times the natural log of 8 times, you're welcome. 60 times the natural log of 8 times 8 to the 10th power. It's going to be a huge number, right? Yeah. Let me go into Desmos here. Let me just switch into Desmos for a moment. So that's pretty good. That's pretty nice. Desmos writes it in a beautiful scientific notation there. I think mine's okay. 60 times the natural log of 8 times 8 to the 10th is 1.3397 approximately times 10 to the 11th power. That should be right. So double check. It's there, and so Desmos does it very nicely. If you use the TI-83 or 84 calculator, it uses like the E notation for scientific notation, but Desmos is pretty good. All right, so that being said, let's go back to the problem here. So here we are. So, okay, that's fine. There it is. And what are the units? The units are cells per hour. Now, here's the thing. An interesting thing. So maybe like in WebAssign, it's going to want you to write your answer as in billions of cells per hour. So what you can do is, I have it written here, but I'll write it here. You can write this as 133.97. Well, actually, hold on. Let me do it like this. I'm gonna do it this way. One moment. Yeah, the eraser works overall better too. It's this updated Blackboard. Okay. So I can write 1 point. Hold on, I don't know what that is. Hold on, I got a lot of junk here coming up. Hold on. This is coming up for you, this junk. What is this? Hold on. Hold on here. Let me clear these annotations and get this junk off here. All right, hang on. Man, I don't know how that happened, class, but let's. Sometimes you hit the wrong button, and you know. All right, this is where we were at. Okay, so, all right. This you can think of as 1.3397 times 10 squared times 10 to the 9th. I can take 10 to the 11th and write it as 10 squared times 10 to the 9th. Now, why would I want to do that? Well, 10 to the 9th power is equal to what? 1 billion. 10 to the 6th is 1 million, right? 10 to the 9th is 1 billion. Now this other part, 1.3397 times 10 squared, you can write as 133.97. So that's how I get this 133.97 times 10 to the 9th. But then that will equal 133.97 billion cells per hour. So after 10 hours, that's the growth rate of this E. coli bacteria. It's growing at 100 at that moment, at the 10 hours, it's growing at a rate of 133.97 billion cells per hour. So what do you think? Is that pretty fast growth rate there? How many are impressed by that? Victoria is, and Masume is, and you know, this is why it's very important to you know, worry about E. coli bacteria. It's very important to worry about it. And we have health department and everything. That, I mean, they're watching out for this stuff, right? They're watching out for that. You know, because it's dangerous. Now, are there any questions on that? I am gonna go to the ebook here to show you a few things there.
More scary is to think that this bacteria is actually in us right now.
Well, yeah, I guess, you know, I'm not an expert on the, I guess I don't know if there's good E. coli or bad E. coli. I guess we do have E. coli in our stomachs, right? Is that right, Clea? Do we have any biologists, people who are knowledgeable about?
Yeah, well, we have it in us, but not exactly in the stomach, but like in our, oh, I forgot, like in our colon. Yep.
In our colon, so our feces will have it.
I guess so.
Okay. Yeah, well, you know, and it's you know, we need it, but I mean, I always have heard it used kind of negatively, but I guess maybe there's some good stuff too, you know. I mean, bacteria, we do need bacteria,
Yeah.
you know, help break things down and stuff. And you know, all the problems in section 7.4. Now, exponential decay would be like, for instance, a radioactive element. How many recall radioactive decay in maybe pre-calculus? Okay, Clea remembers that, and hold on here. Some other folks. Let me see here. A couple people said they did. All right. And so in the ebook here for this section, so we are, let me see, one moment here. Let me go back here. Mohammed, I'm going to show that formula for you, but do you have a question? Or for everybody, I should say, but did you have a good question?
No, I don't. I just had it raised.
Oh, you had your hand raised for the question. Okay, great. All right, no problem. Let me see here. So, got to get to the ebook. Okay, so this is the section 7.4, and the growth models are the growth rate is proportional to the size of the population. Okay, so you can use P instead of Y, for instance. And you know, there's E. coli right there. There's some E. coli. That's what they look like. And if you have, here's what I want to show you, this formula here. The solution of the initial value problem, dy dt equals k times y, where initially you have some initial value. The solution is going to be, it's going to be this. Let me just, one moment. It's going to be this. Y of t equals the initial value times e to the ktth power. Now we derived that. They actually, in the book, they derive that. They start here with the general differential equation, and they go through the steps, separation of variables, and derive the formula. They derive the general formula. We derive the formula for our particular example. Okay, but you certainly, now that you see why the formula is true, you certainly can utilize this formula in section 7.4 to help you. Okay, at least, but now you see, now you recall that formula, y of t equal, how many recall that highlighted formula there? Not the highlighted, but the gray formula in the box from pre-calculus. Whenever you're dealing with exponential growth, exponential decay, you have population growth, you have radioactive decay. How to recall that formula in the gray box there? Sure, you remember that. You've seen that. You've used that. But now you know why it's true, and it's true based on the fact that whenever you're dealing with like certain kinds of population growth and radioactive decay, the growth rate of the amount is proportional to the amount at time t, and then you get that solution. So in the book they talk about example 4, Newton's law of cooling. I'll let you look at that. A lot of your problems in, I think most all of the problems in section 7.4 also have help aids. So I think you're going to be fine on 7.4. That's due this Friday, 7.4. Yes, Clea, question?
Yeah, so when we do the problems, do we have to derive the equation, or we can just use the equation directly?
You can use that formula that you see there directly. I mean, I would of course be delighted if you wrote down the differential equation and separated the variables. But you'll always get some version of that formula. And so, being we've gone through it once, I'm okay if you use the formula. I'm okay for that. It works for the section 7.4 problems, but not necessarily for the 7.3 problems, right? Well, not really for maybe, I don't know if, well, you know what I mean. This 7.4 is very specific types of problems, exponential growth, exponential decay. Good question. Are there any other good questions? Okay, all right. So let me just take a moment here before I set you off to work on classwork. I'm going to call out some names here. So during this classwork break, I want the following people. This is not a bad thing. I just want to mention it. So during this classwork break, I would like Daniel Alvarez, Liliana Biama, let me see, Daniel Cortez Gratakos. So the following people, the names I'm mentioning, if you could please use the classwork time to upload your photo ID into Examity. Okay, it could be driver's license, it could be student ID, passport. If you could load it up into Examity, I would like you to do that. So Daniel Alvarez, Liliane, Daniel Cortez Gratakos, Gabriel Hurtado, Dawit Mengisti, and Helen Ruman. So if you all could please do that during the classwork break, I would appreciate it. And we're gonna take till about 5:40. We'll take an 18-minute break here to give everybody to relax like 5 minutes, and then give folks a chance to work on the new homework that's due Friday. And then those of you that need to upload your Examity, your photo IDs, you can do that. Let me see. Let me take the password off here on that 7.4. One moment here. Once you've uploaded your IDs, the folks that I called your names out, could you just send a chat, just chat it back to me? Send just a chat message to me, I'd be grateful. Okay, so in WebAssign now is 7.4, can you access it in WebAssign? Can you open it? That Claire, that you can, that's okay, great. So let's use this time. We'll take I'll be back like in 5 minutes here, and then we'll have our classwork here till 5:40, and then we're going to move into section 8.1. Excellent, excellent. Oh, I have this on recording too. Okay, great. No problem. I'll stop the recording. Nothing bad.